Mars, a presentation by Ben Klein, Ryan Stobart, and Adam Hester. Mars, along with the rest of the solar system, was formed 4.5 billion years ago through the process of accretion, during early condensation of the solar nebula. Mars is located between Earth and Jupiter and is the furthest terrestrial planet from the Sun, at 1.53 AU. Mars is roughly half the size of Earth, with about a quarter of its surface area. Mars has two moons, Phobos and Deimos, which were most likely captured. Phobos is the largest of the two and is at a shorter distance from the planet. You can see the orbital pattern in the bottom left corner of the screen. Mars exploration began with Galileo in 1610 with the first telescopic observations. Exploration with orbiters began in 1971. These orbiters include Mariner 9, Mars Observer, Viking, and Mars Odyssey. All orbiters were equipped with instruments designed to retrieve data from the Martian surface and atmosphere. In addition to the orbiters, multiple landers and rovers were deployed to the surface to collect data. This map depicts the landing sites of 5 of the American landers and rovers. Perhaps the two most important pieces of equipment sent to Mars were the Thermal Emission Spectrometer, known as TESS, dispatched from Earth in 1996 aboard the Mars Global Surveyor, and the Thermal Emission Imaging System, known as THEMIS, aboard the Mars Odyssey, which reached Mars in 2001. While both instruments perform thermal infrared spectroscopy on the upper decimeter of the Martian surface, the TESS has a higher spectral resolution and a lower spatial resolution. THEMIS, however, has a lower spectral resolution, as you can see in the diagram by the spectral band positions, and a high spatial resolution, which allows for more detailed surface analysis. Once the measured spectra reach Earth, they are compared to a spectral library composed of likely end members through a linear deconvolution algorithm. This algorithm provides a best fit modeled spectrum with a probable percent composition of all end members. This is possible because it was found that the spectrum for each constituent for a rock adds linearly. The linear deconvolution algorithm also provides a root mean square error, which allows for a certain confidence off the modeled spectrum. Mars is separated into two geographical terrains, north and south. They are separated by what is known as a dichotomy boundary. The southern terrain consists of older Milwaukeean age rocks. It has a rough surface area, high relief, large amount of cratering, and consists the majority of the planet's volcanism. The northern terrain is much flatter and has lower relief. The rocks here are mostly Amazonian in age. Quasi-circular depressions support the theory that the origin of the dichotomy boundary is the result of multiple large impacts in early Martian history. Mars consists of two main lithologies, Type 1 and Type 2. Surface Type 1, present in the older, more cratered southern highlands, is primarily composed of basalt. The northern lowlands are composed of surface Type 2 material that could be either an andesite or weathered basalt. Both possibilities are likely with the current spectroscopic data available from THEMIS and TESS. Andesite is less likely because our current understanding of magmatic evolution does not correlate well to a high abundance of andesite on the Mars surface. Magnetic signatures found mostly in the crust of the southern highlands suggest that there was once a magnetic field and plate tectonics on Mars. However, most of these magnetic signatures have been located in Milwaukeean age terrains and suggest that the magnetic field only existed for a short period of time. Additionally, there is no evidence on the Martian surface, such as orogeny zones, that indicate plate tectonics, but rather the crust of Mars is composed of one stagnant lid. The interior of Mars consists of a mantle and core. The core radius is approximately half that of the planet's radius. Recent research by Stewart et al. Demonstrates that the core may be partially or completely liquid. There are two possible core regimes, each of which is dependent on sulfur content. At 10 to 14% weight sulfur, a snowing core will occur. This is where iron and nickel crystallize near the mantle-core boundary and fall to the center of the core. At 14 to 16 weight percent sulfur, the second possible core regime, the sulfide core, consists of iron, nickel, and iron sulfide, which crystallizes at the center of the core and builds outwards. The production size-frequency distribution of impact craters on inner solar system planetary bodies, such as the Moon and Mars, is used to age-date the surfaces of these bodies. It is expected that throughout the history of the solar system, the Moon and Mars underwent a similar amount of impact events. Due to this and precise age dating of returned lunar samples, we can use the size and frequency of craters on the surface to date the relative and near absolute age of terrains on these planetary bodies, including Mars. For instance, On the left side of the picture, there is a heavily cratered Noachian age terrain of the southern highlands. Alternatively, on the right-hand side of the picture, there is a lightly cratered Amazonian age terrain of the northern lowlands. As this picture shows, the southern highlands is heavily cratered and therefore older than the northern lowlands. As evident by the presence of hydrated minerals in old terrains, early Mars had a significant amount of water on its surface. The thicker atmosphere of Noachian Mars would have created conditions more suitable than those of today for large amounts of surface water to exist for extended periods of time. Large impacts, such as those created by Hellas and Argyre impact basins, helped facilitate the loss of much of Martian atmosphere. The result of this loss was the end of rainfall on Mars and the loss of surface deposits of water. Liquid water is only stable with temperatures over 273 degrees Kelvin and when pressures are 6.1 millibars or higher. Such conditions do not exist on the present-day surface of Mars, but could exist just below the surface. For most part, however, the zone where water is present is constantly frozen. This zone, the cryosphere, varies in thickness across the planet with an overall thickening trend over time as heat flow decreases. Some estimates have put the capacity of the cryosphere as high as several hundred meters worth of water if spread evenly over the planet. Mars' standard temperature and pressure conditions vary greatly from Earth's. Standard temperatures on Mars ranges from negative 123 to negative 33 degrees Celsius, and atmospheric pressure has a mean of 0.008 atmospheres, but can vary seasonally up to 25% with higher pressures during the southern summer due to partial sublimation of the polar caps. Occasionally, planet-wide dust storms can occur, such as the one observed by the Hubble telescope in 2001, which can mask most of the surface of Mars. The main type of volcanism on Mars is basaltic. On Earth, these magmas commonly erupt as highly fluid flows. This is also common on Mars, but the lower gravity and atmospheric pressures cause nucleation of gas bubbles to occur easier and at a greater depth than on Earth. This means for the lava to erupt at the surface before it solidifies, the lava source must be extensive. The lower gravity on Mars allows for a longer flow and for it to be more widespread. Because Mars currently lacks plate tectonics, the volcanic pattern on Mars does not match Earth's. These volcanoes are more like mid-plate volcanoes, such as those in the Hawaiian Islands, which are thought to have formed over stationary mantle plumes. Olympus Mons, the youngest and tallest shield volcano on Mars, has an elevation of 21 kilometers and a slope of 4 to 5 degrees. Alba Mons, a volcano with no counterpart on Earth, has a slope of 0.5 degrees and extends 2,000 kilometers north-south and 3,000 kilometers east-west. Syrtis Major is 1,200 kilometers in diameter and has an elevation of 2 kilometers. This is the site of a chemically evolved magma due to the silicate-rich dacite and granite. Martian meteorites have been found on every continent on Earth, except Australia. They were once classified into 3 types of meteorites: shergottites, nacolites, and chassignites. These 3 types have been reclassified into 5 types. The shergottites were divided into basalts and lateralites, the nacolites are clinopyroxene cumulates, and the one chassignite found consists of dunite. Perhaps the most appealing and controversial meteorite is Allen Hills 84001. It consists of orthopyroxene cumulates. Furthermore, pictured in the bottom left is what may be the first fossilized evidence of extraterrestrial life. This, however, has been refuted because of its small size, and also the same form can be created abiotically. The possibility of life on Mars is a subject that has been debated for some time. Currently, it does not appear as though conditions on Mars would allow for life to exist on the surface. It is more likely that if life does exist currently, it would be within the subsurface where geothermal gradient allows for liquid water to be stable. Ancient life, however, may have survived on a warmer, wetter Noachian Mars, and it is possible that fossilized evidence could be found on the surface today if it was rapidly buried in the past. Time and high resolution will reveal all.